Hey folks. So this is the last little bit of the Fourier series packet, which we skipped over in class, but I wanted to take the time to show this really nice property of the Fourier series and also show you a neat application of it. So the property is the so-called Parseval's identity, and it says the following. So if f is an L2 function, and we'll talk about from negative pi to pi specifically, and f has the following Fourier series expansion. So because I'm talking about negative L to L, right, I know that my Fourier series expansion should include both the constant term, the cosines, and the sines. Then the following identity is true. So the L2 norm squared of f, okay, divided by pi, should equal, and you see what's kind of interesting on the, so on the left-hand side, we have the L2 norm, which, right, you're thinking about the integral of f squared there. And on the right-hand side, we have simply an infinite sum of the coefficients squared plus, 2 times the a naught squared. So very interesting little calculation here. And so my first remark is we should think about this as something like an infinite dimensional version of Pythagoras's theorem. And it's really nice to sort of remark on this a little bit because remember, what does Pythagoras's theorem really say? Well, yes, it's, length of hypotenuse, but really it's saying that if I have orthogonal vectors, right, which is what would happen if I gave you a right triangle, right, you would really have orthogonal vectors. Then the sum squared, or the sum of the square of the norms of these vectors, right? I mean, so I'm talking about the magnitude of these things, somehow tells you about the total length of the resultant vector squared. So somehow, yeah, the right-hand side of this is sort of the legs of your infinite dimensional right triangle, and you square all these things and add them up, and that should give you the norm squared of the result of like the whole thing, right? So that's something really interesting going on here anyway, I think. So, okay. So fine, so this is something like a Pythagoras' theorem, and it has sort of two interesting things to draw from it. So first, we know that since we start from an L2 function, that means the L2 norm must be finite by definition. And so this tells us in particular that this series must converge. And that series converges implies that these ANs and BNs must go to 0. So practically speaking, this must mean that just a few terms of the Fourier series must be enough to get good accuracy for, sort of practical computations. And we have seen that, right, in all the simulations we've done in class together, that just taking a few terms of the Fourier series is often enough to get pretty good agreement between the approximations of the Fourier series and the true function itself. Okay, so let's prove this theorem. It's actually not a terrible theorem to prove. So let's start by saying, well, so suppose f is an L2 function from negative pi to pi, and it has a given Fourier series. So f of x equals a naught plus sum from n equals 1 to infinity. And let me just combine all the cosines and sines together. So cosine of nx plus bn sine of nx. Okay. And again, all these sines and cosines are being summed. Okay. So what do I want to do? So on the left-hand side, I want to calculate the L2 norm squared. So what that means is I should square both sides, right? So squaring both sides, I should get f of x quantity squared equals, well, I guess because I'm on the iPad, I can do some nifty little tricks like this. If I duplicate and then pull this down, then I can square the right-hand side as well. And then let me just integrate, right? And then integrate over negative pi to pi. Okay, so what do I end up with? So on the left-hand side, I'll get negative pi to pi integral of f of x quantity squared dx equals. Now on the right-hand side, okay, so I'm going to have this big integral from negative pi to pi of, let me again grab this, So just because I want to write it out twice, let me write one version of it. And then I actually want to paste a second one. Okay. So I'm a little bit out of room, but that's okay. So this times the same thing again, all dx. Okay. So I just wrote the two copies rather than writing it squared. Sometimes it can be helpful to write the two copies next to each other. And all this is being integrated dx. Okay. Wonderful. So the hope is I can make some progress here without, going too over the top with all these calculations. So the left-hand side, of course, is none other than the L2 norm squared. Okay, so that's nice. So I can sort of simplify the left-hand side immediately. Equals. Now, on the right-hand side, I'm going to, pull the integral into all these infinite sums. But before I do that, I need to sort of do this massive distribution problem. And so what we just need to remember here is that most of the terms when I integrate will go to zero. Again, I'm exploiting orthogonality. Okay, so the thing here to notice is that upon distribution, most terms will equal zero. And so we can sort of spend our time just thinking about which terms will not be zero. So for example, when I multiply the a naught times the a naught, this is when I integrate not going to necessarily be zero. So let me keep that term. So the integral from minus pi to pi of a naught quantity squared dx will stick around. Plus, okay, let me think about some of the cosine terms. So if I take this cosine term, that looks very suspiciously like the color I just used. So let me try another color. So if I take the cosine terms, if I were to multiply this by, I guess I didn't say this for the last one. So if I take this a naught term and multiply it by, say, the cosine terms and then integrate, I know those are all going to go to zero. Okay, I'm exploiting orthogonality of constants against cosines or constants against same logic for sines. So the only term that sort of sticks around when I multiply out this a naught with the second infinite sum is the a naught times a naught. Okay, so that's why I only wrote one term. So same thing's going to happen when I do the cosines here. So I have this an cosine term. When I distribute any of these terms to the second part, well, when I distribute it to the a naught, it'll go to zero when I integrate. When I multiply against the sines, again, it'll go to zero when I integrate. And if I take any of these cosines, multiply it by the wrong cosine, so for example, cosine of 2x times cosine of 4x, right? Those are orthogonal, so they'll go to zero. So at the end of the day, all I'm going to be left with is when a cosine term is multiplied by exactly that same cosine term, which I can write as the so I'll do the sum from n equals 1 to infinity. So I do an times an, so that's going to be an squared, and then cosine squared of nx, and this is going to be integrated from negative pi to pi dx. Okay. And again, you think about all the possible distributions that I could send this an cosine nx to, they'll all go to zero unless it's perfectly matched up. Okay. And of course, I need to consider all the different n's, right? N equals 1, 2, 3, right? So that's why I still have an infinite sum. But if that makes sense, then hopefully the last part will also make sense by the same logic. I'm going to do exactly the same argument for the sines to get a sum from 1 to infinity of bn squareds sine squared nx, and again, integrate each of these from minus pi to pi dx. Okay, so most terms go to zero, except for when I multiply the cosine by exactly the same cosine or the sine by exactly the same sine. We've seen this idea before. Okay, so then we can actually calculate, right? So, the constants an squared, the bn squared, those can all pull out of the integrals. And so we can actually calculate, right? We can calculate the integral from minus pi to pi of cosine nx dx. It turns out to be exactly the same thing if I'd integrated minus pi to pi of sine squared nx dx. And if you sit down and calculate that out, you probably need to use some trig identities as well, right, for this. But you'll see that it always equals pi, no matter the value of n. So thus, when I sort of put all of this together, what do I get? I get the L2 norm of f squared on the left equals, oh, I didn't evaluate my a naught squared integral, but that's not a problem, right? That's a constant. So I'm going to get a naught squared times 2 pi, right? Plus the infinite sum from n equals 1 to infinity of, so I have my a n squareds pulling out. And then the integrals all turn into pi's. So I'll leave that. Plus, now the green term, the sum of the signs. Same thing, the bn squareds all pull out. The integral of the sine squared will again become just pi. And you see if I divide everything by pi, I arrive to my desired equation, 1 over pi times the L2 norm of f squared equals 2 a naught squareds plus the infinite sum from 1 to infinity of a n squared plus b n squared. We're done. So a very nice proof. It somehow maybe looks more complicated than it really is. Once you square both sides, you're sort of squaring this infinite sum on the right. When you integrate, you just have to think about most terms being orthogonal, which means you know they won't matter when you try to integrate or when you try to add them all up. And so we should only keep the terms which we know will be non-zero upon integration. Okay, and that's sort of what I had to do here in this step. Okay, so how do we use this theorem? Well, one of my favorite applications of Parseval's identity is to solve the Basel problem. So we talked about this briefly in class. We know that this infinite sum of 1 over n squared does converge. This is the p-test from Calc 2. The question is, what does it actually converge to? Well, it turns out to be a beautiful application of this identity we just proved. So the big idea here is to take the Fourier series of the right function. So the right function in this case is to consider f of x equals x. That's it. And let's see what happens. So in particular, I'm going to consider this function f of x equals x. And again, because I'm going to do Parseval, let's do on the interval negative pi pi. Okay, so let's begin by first calculating the Fourier series. So let's find the Fourier series. Now, in general, I should calculate both cosines and sines, right? All of the coefficients. I will leave it to you to notice in this case that I can ignore, or so in other words, the cosine terms will all have 0 coefficients. I'll let you think about why. So all cosine terms are 0 coefficient. So let's only compute the Fourier series of the sine terms. So the sine coefficients should be given by 1 over L integral from minus L to L f of x times sine of nx dx. Okay, so I'm just plugging in my formula for the coefficients of the sine series. And what do we get when we plug this in? Well, again, let me skip the dirty details. This is all integration by parts. You should get 2 times minus 1 to the n plus 1 all over n. This may look familiar, right, from class. You can always think about why this is exactly the same formula we got when we did 0 to pi. That shouldn't be super surprising from what we saw in class. But okay, good. So once we know this, then we know, so thus, x, the f of x, right, equals the Fourier series, n equals 1 to infinity of 2 times minus 1 to the n plus 1 over n and then sine of nx. Okay. That's the Fourier series expansion. And again, you can think about this on the interval minus pi pi. Okay. So now, once I know the Fourier series, we can use Parseval's identity. So by Parseval, we know the L2 norm of the left-hand side. So I should take the L2 norm, so 1 over pi, times the L2 norm, which is integrate x squared from negative pi to pi dx. Again, I say L2 norm, it's really the L2 norm squared, right? We're not doing the square root here. Equals, now on the right-hand side should be the sum, well, let me just write it all out, right? A naught plus the sum squared 2, n equals 1 to infinity, a n squared plus b n squared. And so in this case, we know that all of the a naught and a n terms are 0. And so all I have is the infinite sum from 1 to infinity of the bn's, which we just saw were 2 times minus 1 to the n plus 1 over n. But don't forget to square. Okay, just the coefficient term bn squared and then summed. Okay. Now this is an equation we can work with. 1 over pi times this integral. I can evaluate that in a second. But let me start on the right-hand side here, this infinite sum. If I square everything, I'm going to get 2 squared becomes 4. Notice minus 1 to the n plus 1. It doesn't really matter if I square this is all going to be positive 1. And then all over n squared. What happens on the left-hand side? I get 1 over pi times the antiderivative is x cubed over 3, evaluated from minus pi to pi. This equals, you know what, let me pull the 4 out, sort of working my way slowly towards that infinite sum, which I was hoping to see. And now I feel pretty close to the end. On the left-hand side, I'm getting 1 over pi times, let me plug in my sort of fundamental theorem stuff. So plugging in minus pi, it's going to be minus a minus, so plus pi cubed over 3 again. This equals 4. Oh yeah, this is looking pretty good. So now the left-hand side, I'm going to get one of the pi's cancel. So I should get 2 pi squared over 3 equals 4 times this infinite sum. But now dividing everything by 4, I arrived to my final answer. The infinite sum of 1 over n squared should be pi squared over 6. That's it. So it's a really it's a nifty idea, right? That I can get the actual limit of this infinite series by just taking the Fourier series of a well-chosen function, right? And applying Parseval to it. So you see, we started by getting the Fourier series. By applying Parseval, it gives us an equation relating the L2 norm of the function to the infinite series of those coefficients. And so just plugging everything in and evaluating, you arrive to this really nice little equation down here. So some things you can think about are, well, what if I did this exact same thing, but not for the Fourier series f of x? What if I did f of x equals x? What if I did like x squared or x cubed? Would I get different identities? Like what would those identities look like? So I'll leave that to you to explore and see what happens. All right. Hopefully you found this interesting, and I'll see you in class.